For the remainder of the semester, we're going to be talking about the way the universe is going to end. A lot of the things we've talked about in here have been the ways various things in the universe, you might say, are trying to kill us. For instance, when the sun dies, we get burned up by the sun. You could wonder if we're ever going to get sucked into a black hole. Probably not. Are we ever going to get hit by a supernova? Probably not. But those are ways that the universe might try to kill us. Meteors, clearly, are something that are trying to kill us. Well, we know for a fact that someday the universe is going to end. The universe is going to come to an end just like it had a beginning. And the question is, how is that going to end? So whenever the universe goes, we go too. But to understand the end of the universe, we also have to understand the beginning of the universe. And that means that we need to study the most distant objects in space. This is a famous picture from the Hubble Space Telescope called the Hubble Deep Field. It's one of the most famous pictures by the Hubble Space Telescope. And this is a very, very, very small area of sky. If you held up a dime at arm's length, President Roosevelt's eye would cover about as much space as this picture covers. So you're really seriously seeing something zoomed in. And almost every object in here, with the exception of this, is an entire galaxy. There's another star. These little bright things with little spikes are stars. But everything else is a galaxy. An entire galaxy with hundreds of billions of stars. And this is just a tiny area of the sky. And you can think about how many galaxies there must be throughout the universe if this is how many galaxies there are in just this tiny area. These are also some of the most distant objects that have ever been photographed. These are very, very, very far away. Why do we want to study things that are far away? Well, remember back at the beginning of the semester, we talked about light travel time. If we see something that's far away, we're seeing it the way it looked a long time in the past. So if these things are 8 billion, 10 billion, 12 billion light years away, which they are, we're seeing the way the universe looked 12 billion years ago. If we want to understand the beginning of the universe, we need to understand the most distant objects in space. And those are these very, very distant galaxies. Now, of course, if we want to be sure we're doing that, we need to know about the distances to galaxies. And this is the subject of this lecture. So in space, it's very difficult to measure distance. We've talked about this a little bit in class. We talked about parallax, for instance. We learned how parallax could be used to measure the distance to stars, and you even simulated that in lab. Unfortunately, as you found, that only works for very, very nearby objects, because otherwise the angles are just too small. We can't observe them. So parallax doesn't work for more distant things, like these galaxies that are back at the beginning of the universe. So for more distant objects, what we use are different things that are called standard candles. Now, obviously, they're not candles, but this term came up from a time period before electricity. So what a standard candle is any kind of object in space whose luminosity is something that we happen to know and whose apparent brightness we can measure. And then we can calculate the distance based on the apparent brightness formula. We know that apparent brightness equals luminosity over 4 pi times the distance squared. We've used that formula before. And so if we know the apparent brightness, we know the luminosity, we can find the distance. And you've done labs with a couple of these already. For instance, if we have a cluster of stars, we can make an HR diagram, like this one over here. This is an HR diagram. And it's got 2 different clusters on it, the Hyades and the Pleiades. We know what the luminosity of the main sequence is supposed to look like. We have studied the HR diagram very, very thoroughly. We know the luminosity of stars on the main sequence of a given temperature. So if there's any difference between where the clusters are located on the HR diagram, then it must be due to a difference in their apparent brightness. And if they've really got the same luminosity, and we think they do, then that must be due to a difference in distance. If we know the luminosity of the main sequence, we can measure the apparent brightness of the stars on the main sequence in the cluster, and then we can calculate the distance. And you did this in one of your labs, so you've got some experience with it. We like the cluster because it's got lots and lots of stars. You can't be sure if you just have an individual star sitting by itself and you measure its apparent brightness and its temperature, you can't be sure that it's a main sequence star immediately. You need to be able to know the luminosity to plot it on an HR diagram and see if it is truly a main sequence star. But for a cluster, we have enough stars that the only difference between them is their luminosities, because all stars in a cluster are at the same distance. And so we can feel confident that when I look at a main sequence of a cluster, I can be getting truly main sequence stars, and then I can find the distance. Well, that's great, except that we can only measure the apparent brightness and temperatures of clusters of stars in a cluster for stars that are in our own galaxy. This doesn't get me to other galaxies, so it's a problem. Also, as you found in the lab, it can sometimes be kind of hard to match it up. There's a lot of uncertainty in these measurements, so it's kind of a tricky one. It works, but it's kind of tricky. Another one that you haven't seen before is what are called Cepheid variable stars. Now, variable stars are ones that change their apparent brightness over time. And it turns out that these Cepheid variables are a particular kind that change their brightness in a predictable way. And it just happens to be the case that the amount of time it takes for them to change their apparent brightness is related to their luminosity. That's what this graph shows. So if you have a Cepheid variable star who changes its brightness in 10 days, well, then you can say that its luminosity is about 2,500 times the luminosity of the sun. So in that case, we know the luminosity, and you can find a sort of average apparent brightness, and from that you can calculate the distance. And those we can actually see in some nearby galaxies. For instance, the Andromeda galaxy, we can find individual Cepheid variable stars, and we can calculate a distance based on that. And that's really good. But for more distant galaxies, if you think back to that first slide that I showed in this video, you can't pick out individual stars in those galaxies. They're just too far away. So this doesn't work really well for the most distant ones. What does work for the most distant ones are white dwarf supernovas. And you did do this in lab too. You'll recognize graphs that look kind of like this. White dwarf supernovas, when they explode, brighten and fade in a predictable way. This is because they all occur in exactly the same way. Right when the white dwarf hits 3 solar masses, it explodes. And so because they all happen in exactly the same way, they have this predictable brightening and fading, and the difference between them only has to do with the distance between them. So this is something we know the luminosity very accurately for white dwarf supernovas. Very, very, very accurately. And we can do one of these graphs and match it up with a theoretical prediction, and we can very accurately find the distance. And this is great for those really distant galaxies, if there happens to be a white dwarf supernova. White dwarf supernovas, when they explode, are so bright that they're as bright as the entire galaxy. So we can see them. We can pick out the individual star. We know it's in that galaxy because there wasn't an individual star there before. If it was in our galaxy, we would have seen the individual star there already. So if one of these goes off in a distant galaxy, we know that the star is in that galaxy and not ours. And so we can feel very confident that we're looking at something in this very distant galaxy. And supernovas are so ridiculously bright that we can see these in extremely distant galaxies. Of course, the problem is you have to wait until there's a white dwarf supernova in that particular galaxy, and until that happens, you don't know the distance. But when it does, you can get a very, very accurate distance. And this is going to be important later on when we're trying to figure out what the ultimate fate of the universe is. We can use white dwarf supernovas to study that. So this is going to be very important later on.